codes. So just wait a second. How do I? Okay. So just as an outline, I want to make the point that very often it's important to choose the best method for the problem that you want to solve. And I will try to explain to you what Lagrangian hydrodynamics and specifically SPH is very good for. Then I will do probably most of the talk will be on Newtonian SPH so that you understand the method. And once you've understood the method, it should be relatively straightforward to translate this to the GR case. If I then have time, I can show a couple of examples and then summarize. So just to say this from the beginning, I like particle methods very much. I think they're very cool. But don't get this wrong. Whatever I say positive about SPH, I know there are wonderful other methods around. And as I said, you have to pick the right method for the problem. Say it's like cycling. Say if you want to win the Tour de France, you probably wouldn't do it on a mountain bike. Maybe you can if you're a Superman or Superwoman, but it's certainly easier with a good bike. And the same thing the other way around. If you want to become the world champion in mountain biking, you'd probably not pick a Tour de France bike. So it's important to pick the right thing to make your life easy. Okay, so now why SPH? Maybe just as a very first basic thing, the most commonly used the methods probably for gas dynamics are, I would say, finite volume schemes, very often on Eulerian Cartesian grids. And then there are Lagrangian hydrodynamic schemes. One typical one in astrophysics is smooth particle hydrodynamics. And there the idea is that you model the fluid as a set of overlapping particles and spherical particles usually, and for reasons that we will just see a bit later. But having said this, there are really plenty of ways how you can do a Lagrangian Lagrangian hydrodynamic scheme, and in particular also with particles. But you can also do this with meshes. So keep in mind, this is just one special thing. There are other ways to do this, but from now on, for the rest of this lecture, I will talk exclusively about SPH. Now, one of the major selling points is, and keep in mind, I'm talking initially now just about the Newtonian version, we can have exact conservation of mass, energy, momentum, and angular momentum. And that means even at finite resolution. So you can really build in these conservation laws into the discretized version of the equations. And that makes it very powerful because you always stay pretty close to what nature would do just because you have the same conservation laws built in. Now, one thing that in my opinion is not always appreciated enough is that apart from doing shocks, also advection has to be very accurate in a simulation. And don't get me wrong, shocks are definitely very important, especially in astrophysics, because there you have gravity, and gravity can accelerate gas to velocities that are much larger than the sound speed. So you definitely expect shocks to occur, and just maybe for the non-experts, also sound waves can steepen into shocks. So you can't always be sure that not a shock would appear. So this is understood. Shocks are important. But the other thing that is also very important is advection. And what do I mean by this? This is just an example. This is a very good adaptive mesh refinement code, the Flash code. And what this will show is a star which is in hydrostatic equilibrium. And the only thing the star does, it is moving with a constant velocity across the grid. And of course, the star shouldn't bother where we place our grid or how it moves with respect to the grid, but it actually does. So if you look at this, then you see the star deforms a little bit, and here you see these plumes appearing. And of course, these are spurious plumes. So this is something that is physically not there. And of course, you can always argue, well, this goes away with resolution, and this is, of course, fine. But of course, in practice, you often don't have as much resolution as you would like to have, and therefore it would be nice if you could avoid such problems in the first place. Now I'm showing here an example with the Lagrangian method. Like this is a relativistic SPH code. And the problem that I'm showing is actually substantially harder. So the problem that I'm showing is a high density triangle that is moving at a Lorentz factor of close to 71 through a box with periodic boundary conditions. And you see there's zero change. There's nothing that is happening despite the fact that we have these edges here. And this is something like a free lunch for a Lagrangian method. The method doesn't have to do anything at all. It's just moving. As long as your ordinary differential equation integrator works, the system has nothing to do. So if you have some property in this context, interesting, maybe something like an electron fraction or so, this is just sitting on a particle. And if the particle moves, the particle doesn't forget about it. So it's really a trivial problem for such a Lagrangian method. The punchline here is just in the Eulerian case, advection is resolution dependent, while in the Lagrangian case here with SPH, it's essentially exact. And what I'm showing here, this is just 7,000 particles. So it's a ridiculously low resolution. So it's just not a hard problem for this type of method. Now something else. Why is it good? One of those things is with Eulerian hydrodynamics, and as I said, there are wonderful methods for many, many questions, but there are, of course, problems here and there. One of them is vacuum, and often people talk about the atmosphere, but this actually really just means you have a background medium in which the real fluid is moving. And the neutron star surface is just a very difficult place because there the density drops by orders of magnitudes within just a few hundred meters. So it's a tricky issue. But what a typical Eulerian method does that, it identifies the sharp surface as a shock, and then it does what it should do in the case of a shock. It produces entropy, and that means you're pumping in entropy in the surface, and that means you're blowing spurious winds, but these are really just spurious winds. There's no physical reason for them. And if you now look at similar things, for example, with SPH, for vacuum, there's just nothing you have to do. Vacuum just means you have no particles. And you don't have to do any special treatment of the neutron star surface. It just adjusts to hydrostatic equilibrium. And you see here, this is just close to a merger where I show really every particle. And you see the surface remains very smooth and well behaved. And this is actually an easy problem for this method. Now, maybe another thing to say about this background medium, this is something that, of course, also costs computational resources. So even if you're not interested in vacuum, you have to simulate it. While here with the particles, there are no particles. You have nothing to do. So it doesn't cost anything to have a lot of vacuum around. Now, one example, which I would claim is probably not doable with Eulerian code, but if you think otherwise, please prove me wrong. So this is an astrophysical example where you have a binary system. You see these two stars here, two massive binary systems, and you have a black hole of 1 million solar masses sitting at the origin. And the stars are now moving on orbits so that both of them are disrupted by the black hole, one after another. And so this is an example here. Now you see the first star. It's being disrupted and stretched. Now the second star is being disrupted. Now you see they move to the boundaries, but this is just for the movie. There's no boundary in the simulation, and I'm now just zooming out for the movie. And now you see the stars are really stretched into these very thin spaghetti-like shapes, and the inner bits are moving towards the black hole. The outer bits are moving away to infinity. At some point, the accretion streams here go around the black hole, and then you start some accretion fan appearing here. And otherwise, so here where, if you can see my mouse, here you see an accretion fan appearing. But you also see here you have this very nice, well-defined structure, and this is given by the balance of pressure and self-gravity. And just to stress this, so here you see the major advantages, and one is geometric flexibility. So there's no grid or anything. The particles can just go where they want to go. Advection is exact. We are not bound to any computation volume, and the case when I'm saying vacuum is vacuum also doesn't cost anything. Just to also state this, the stars that you have seen in the initial frame, so just those little two dots, they are now something like 10 to the minus 9 of the volume that you see right now. But this is not an issue because the only thing you're evolving is the particles. So this is just kind of like my sales pitch for the particle methods. Now I try to explain the method itself. And as I had said before, you replace the fluid in a sense by a finite set of particles. And those particles, they carry with them some kernel function, which you usually call W. And this kernel function, a typical shape looks like this. So it's a bell-shaped kernel. It goes to 0 at a finite radius. And where this happens is set by a quantity called smoothing length. And you need this kernel function to calculate, for example, smooth approximations of quantities and to calculate gradients. And one of the things that is really nice about this is that you can formulate the motion of the particles in a way that they conserve by construction mass, energy, momentum, and angular momentum. And of course, this is not all my invention. There's a lot of work that has gone into this. There are lots of pretty big reviews. One that I will refer to a couple of times is an update of my living reviews in computational astrophysics, which should appear on the archive pretty soon, which is pretty big, and maybe most of the things you want to know are in there. So now let's start with Lagrangian hydrodynamics. So just like Eulerian hydrodynamics, of course, you have essentially just conservation laws. You have the conservation of mass, momentum, and energy. And to close the system, you need something like an equation of state. I do everything here as simple as possible. So I will usually neglect gravity, and I pick the simplest equation of state if I need one. So just some polytropic type of equation of state. And so one thing that you maybe are wondering about is, well, this time derivative here on the left-hand side, what is that? Well, that is the Lagrangian time derivative. And you get there if you just draw a little sketch and then you say, well, think of a fluid blob that has some properties at some position r at some time t. And then it moves with a velocity to some new position. And if you then compare the properties that it has here with here and take the limit of delta t going to 0, then you find that the Lagrangian time derivative is the Eulerian time derivative plus some advective term here, which is given by this v dot nabla operator. So this is always when I write these type of time derivatives, this is what I mean explicitly. Yes. So now the question is, well, if these are the equations that we try to solve, how can we do this so that hopefully we get exact conservation? So for that, we need a little bit of kernel interpolation. And what you normally do to get to a discretized SPH evolution equation set, you start with an integral kernel smoothing. And then at some point, you have to translate the integrals into sums. And then you need particle volume elements here. Now, the basic function, how you would do this is if you have some function f that is your original function, and you say now for numerical purposes you want the smoothed version of that, then this is given by just folding this with this kernel function. And here this h, which is indicated here, this is a smoothing length, so this determines how far out your kernel is reaching, and it also means on later on how many neighbor particles you are including. And just from this expression here, you see immediately, okay, if this should make sense, so here we're integrating over a volume, that means the kernel function must have the dimension of 1 over a volume. Also for this to make sense, it should be normalized. Also for this to make sense, if you say, well, you make your smoothing lengths smaller and smaller and smaller, that means in this limit you want to recover the original function. So that means this kernel function should have in this limit the delta property. You ideally want a compact support so that you don't have to, so that not every particle interacts with all of the other particles, but just with a nearby set of particles. And actually the kernels, since sometimes you need derivatives, the kernels should be smooth functions. Otherwise, this can introduce some noise. Okay, now the second step I said is discretization. So you need something like a volume element. The most straightforward choice is that you say, well, if the particle has a mass and if the particle has a density, then I have a volume element, but you can do other things, which sometimes may be interesting, but I can't go into this here yet. And then say, just with these principles, you have then a typical function approximation looking like this. So if you're at some position R, you have to figure out what are the neighbor particles and then take the volume elements, multiply here by this function at the particle positions. So this label B is over the particle positions. And then you need to evaluate this kernel function here. Now the next thing you have seen, if you keep in mind the momentum equation, for example, this had on the right-hand side something like a minus gradient of P over rho. So you need definitely some prescription for the gradient. And the simple thing you can actually do, which is still useful, is to just apply the Nabla operator to the above approximation. And since the only thing that depends on R is the kernel, then you just get this function here. And that means you have just a nice formula for the gradient that you can just write down like this. Okay, so and these are already the basic the basic ingredients with which you can do quite a bit. Now you can say, well, so far we haven't said how we get any of these things, these densities, but you could now just try to use this function, typical function approximation to the density itself. And if you do this, then you just see, well, actually, the density here drops out. And what you find then is this formula here. And if you now talk about a particle A, so this is the one that I've marked here in blue, then you have to figure out what are the other particles that are inside the support of my kernel function. And then you're essentially weighting the mass of these neighboring particles with the kernel function. And just as we had said before, the dimension of the kernel function should be 1 over a volume. So that means we have a mass over a volume, of course, that is dimensionally correct. And that means we have actually a simple but very robust way to estimate the density. Now, if we now decide, and that's a decision, that we want to keep the masses fixed, then we have mass conservation built in by construction. Then we just have the same set of particles, each keeps its mass, so there's nothing that can be lost. So exact mass conservation. Another thing that is actually worth stressing is you usually use positive definite kernels here. And that means this sum here gives you always a non-zero positive value. And that means it's always safe to divide by 1 over a density at the particle position, because the particle itself contributes to this sum. So at the minimum thing, even if there's no other neighbor, which should never happen, but even if it was the case, then you would still have the contribution from the particle itself, which is non-zero and positive. But this is just, again, a choice. If you want to solve the continuity equation explicitly, this is another thing that one can do. Okay, so now we have the basic principles, and now we can get already a first version of SPH. So you can now just say, well, let's take the mass conservation. And as I had said, if you want to solve this, you can. But the more robust and simpler way is to just use this summation prescription. And then we have essentially mass conservation built in. The next thing was, in the simplest form, our Euler equation or momentum equation. And you could start straightforwardly discretizing this minus gradient P over rho, but then you would find something which is not conservative. And there is now a simple trick, and this is just, well, you just replace this expression by one that is mathematically identical, but gives you a different discrete version. And if you use this one here, then you find the discrete Euler equation in this way. And here you now have the particle velocity and the Lagrangian time derivative of it. And you find this by summing over the neighboring particles. Here you have a kernel gradient, and here you have a PA over rho A squared and a PB over rho B squared. And just whenever I write something like RAB, I mean this is actually, well, the absolute value here of the vector RA minus RB. Now you can do the energy equation, and just to keep in mind here, this here is essentially just the first law of thermodynamics written on a per mass basis and assuming that you don't produce entropy. So just if we talk about ideal gas dynamics, this is the thing we start from. And you can also straightforwardly discretize this, and then you find a similar equation. Now this U, I'm not sure I've said it, but it was on one of the previous slides. But this is internal energy per mass. And this evolves then, well, according to this formula. Again, we're summing over neighbor particles. Again, here this just means VA minus VB, and this is dotted with the gradient of the kernel function. And with this, this is already this is already a valid equation set that conserves everything by construction. Now, maybe saying this a little bit in more detail with the conservation, where this comes from. We had just said before, if we use this summation prescription and keep the masses fixed, then the total sum of the masses is fixed. So this box is ticked. Then I haven't said much about kernels yet. For now, I just want to restrict myself to always use radial kernels. And that just means that the kernel function just depends on the absolute value of this distance here. And if you use such kernels, then you find if you take the gradient of the kernel function evaluated at RAB, but you take the gradient with respect to particle A, this is the same thing as taking it with respect to particle B, up to a minus sign. So this will be very important, and as you probably or maybe can guess already, this is then to implement Newton's third law, actio equal reactio. The other thing that you find then is that the kernel gradient is parallel to the direction, to the line connecting two particles, and this will be important for angular momentum conservation. So if you now go to the momentum conservation, one thing you can do is you say, well, let's look at the force that a particle, oops, that's the other way around, that a particle B exerts on a particle A. And then you just take our momentum equation from before, have to multiply by a mass. And then you see the first term here is symmetric in A and B. And the second one here, this is anti-symmetric because we have used these radial kernels. And that means this is the same thing for the force from the particle in the other direction. You just have a minus sign. And this gives you then this gives you Newton's third law. If you now then add up all those changes in momentum, then you find, well, you have this double sum over something that is symmetric in A and B and something that is anti-symmetric in A and B. And then you can just, if you don't believe it, and just write down all the terms. Then you see for each term, there's an opposite term that cancels. And so the total sum of that stuff is 0. Now, for energy, you can do the same thing. As I said, we look just at the simplest possible case. So we have the internal energy and the kinetic energy. Take the time derivative, then you see, well, this is our energy equation. Here we can use our momentum equation. You put it all in, then you find something like this. Again, something which is symmetric in the indices and something that is anti-symmetric. So also this sum adds up to exactly 0. So this box is also ticked. Now you can do the same thing for angular momentum. There you look at the total torque and you sum up all the torques. And since you have this double sum here, you can just decide, well, just make 2 sums, divide by 2. And now in one of the sums, we just relabel A and B, which we're summing over both of them. So that's fine. But if you do this, then you see that you can write this in this way. And then what we will use here is what we had seen also before, because we have these radial kernels and the The force is proportional to the kernel gradient, and the kernel gradient points in the direction of the line connecting the two particles. And then this cross product gives you zero. So you have also exact conservation of angular momentum. And this is then a very simple way, and historically, I think it's the first one to have exact conservation of mass, momentum, energy, and angular momentum. Okay, now you can do a similar thing, but much more elegant. And this is, you can actually derive things from an ideal fluid Lagrangian. So, and again, the most simple case, you could, for example, if you want, you can do this by also putting in the gravitational potential, and then the exercise is the same. You just get a bit more complicated terms. But what you do here then is just as before, you replace the integral by the summation. Then you have these quantities here. And then what you apply is your Euler-Lagrange equations, which then gives you the momentum equation. Again, you use the first law of thermodynamics. And then you find a slightly different form of the equations. And they also have small corrective terms here, which I will not talk much about it because they're not terribly relevant for the rest of this. And you see now you have a bit different equations, but they obey the same symmetrization laws with these symmetric and antisymmetric terms, and you can also add them up so that everything adds up to zero. So now I haven't said much about the kernel choice. This is something that you can choose, of course. And traditionally, there's a kernel which is the simplest one that actually ticks the most essential boxes, and this is a cubic spline kernel. But for many practical purposes, this is actually really not a good choice, and there are much better kernels around. And if I'm saying here after personal experience, this is really after literally hundreds of tests and simulation experiments. And say, in my experience, the best kernels are these harmonic-like kernels, which have this type of shape. And maybe even better are these Wendland kernels, which are due to, I think it's a PhD thesis of Holger Wendland, which have these types of shapes. And they have actually really nice properties, these Wendland kernels. So they, in particular, as the particles move, they move in a very nice and well-distributed way, so hardly without any noise. They have a couple of other very nice properties. But if you want to use these high-order kernels, you really need large neighbor numbers. Otherwise, you have a very bad density estimate. But if you have large neighbor numbers, you get a very good density estimate. Okay, then there are lots of other topics that are relevant in practice, but I don't have time to talk about them very much. And these are topics like how do you treat shocks? There are other ways to calculate gradients that are much more accurate, for example, how you adapt the smoothing lens, and so on and so forth. There are many things that are practically relevant, but a bit technical. But as I said in this review, they are described in a fair amount of detail. Okay, then from there, I would say we now know enough about the method itself so that one can start to apply this to the GR case. And this is now very much oriented at our code, Sphinx BSSN. And we had decided at some point to start writing this thing from scratch, which, well, I don't know, was a good idea or not, but it took, in any case, it took a lot of work, and it turned out to be more complicated than we thought initially. But if you're interested in the details how to do this, this is described in a lot of detail in these papers. And maybe if you're interested in a starting point, there is this book which came out this year, and I think there's also a chapter on the Einstein Toolkit in it, and there's also a chapter on our Sphinx BSSN code. And Sphinx, by the way, stands for Smooth Particle Hydrodynamics in Curved Spacetime. Okay, so now if you really want to go through step-by-step derivation, probably the best starting point here is where really every step is shown, is in this 2009 paper. And the idea is here now that one does the same thing as one has done in the Newtonian case, starting from a Lagrangian. And here the Lagrangian would contain the energy momentum tensor and the four vectors, and of course it needs to know about the metric. And then you have, as in every numerical method, you have the choice, which variables do you actually want to evolve? And what we're evolving here is the canonical momentum that comes from the Lagrangian and the canonical energy. And these are, of course, combined quantities of the things that we're really interested in. So the things that usually are called primitives. So these are things like densities or velocities. These are the things that we want. Normally, we don't care too much about things like canonical momentum per baryon because probably none of you, and me neither, has a good intuition about that stuff. So, and that means we have to do a thing that you also have to do in Eulerian relativistic hydrodynamics, which means you have to recover the primitive variables in a numerical method, which can be a bit cumbersome. Okay, then we use the same, well, if you want to call them golden principles as before, that we say, well, we have baryon number conserved. This is then very similar to our summation over the density that I had shown in the Newtonian case before. We again have Euler-Lagrange equations, and again, we use the first law of thermodynamics. And if you then go through the algebra, which is now substantially more cumbersome than before, but once you have done it, you find equations that look actually relatively similar to what we had seen before. So you have a momentum equation. This replaces our dv dt that we had before. We have an energy equation. This is now, as I said, canonical energy. So this contains both kinetic and internal terms. And then we have baryon density conservation, and this looks very much like our density summation in the Newtonian case. And you see the first terms here, there are summations over neighbor particles. And again, you have things like p over rho squared, or this rho here in the GR case, I call this n in this case. Then you have, of course, the metric. You still have these grad h terms, which you can think of them as being 1 for now. And then you have kernel gradients. Again, you have the things symmetrized just as before. And you have similar terms here for the energy. And then you have a second set of terms here, and this contains the energy momentum tensor and derivatives of the metric. And this is, of course, the accelerations and the changes coming from the space-time. And as you see here, this is for evolving the particles. So the particles need to know about the metric. So, and since we want to evolve the metric as well, we evolve the metric on a mesh, but use particles for the hydrodynamics. But also, if you want to evolve the space-time, you need the T mu nu as a source, and this is something that you know at the particles. So, and then you see, well, these terms, they need something from each other. And to get this to work, you actually really need an accurate information exchange between particles and mesh. So really in both directions, and you need to do this at every Runge-Kutta substep that you want to simulate. Okay, space-time evolution, there is nothing special we do here. So this is, we use a pretty straightforward BSSN formulation on an adaptive mesh. And since very recently, we've also added some constraint damping terms. Say the metric we had said the particles need it and the mesh has it. So we have to see how we map the metric to the particle positions. This is done by a fifth order Hermite interpolation. And the reason is just then we have continuous second derivatives. And that means if a particle crosses from one cell to another, there is no little glitch or anything. So we avoid noise being introduced by this high order interpolation. The more complicated part is actually how we map the particle properties to the mesh. And wait a second, that's the other way around. Sorry, this should be particle to mesh. And the idea here is think of the particles as these blue dots, and now think of a grid point that is somewhere in between. And now we know the T mu nu, for example, at the particles, and then we want to know what is the best version of T mu nu at this point that agrees best with the surrounding particles. And the strategy here is that you then just say, well, let's assume all the particles here, they are given by some function. And then you do a Taylor expansion around this grid point here. And if you do this, then you find just writing down the Taylor expansion explicitly. So one part of the Taylor expansion is just looks like a polynomial basis. So these are the terms delta x times delta y times delta z or so. And then you have prefactors. And these prefactors are things like, well, for example, gradients, second derivatives with the corresponding numerical prefactors, but you can collect them in something which you would call then, well, coefficients in this expansion and optimal coefficients and optimal at this grid point. And the way you calculate this is by just minimizing an error functional here. So then you find these coefficients, and that means you have a good idea about what the coefficients are. Now, I had just said, well, Taylor expansion, but up to which order? And this is, of course, something that you don't know beforehand. And if you would just think about, say, a merger or two neutron stars close to merger, you would probably think, well, in the center where everything is well resolved and you have no boundaries and nothing, probably here you would want to have a high order, but maybe at the surface, this is not a great idea because high order polynomials and sharp transitions usually lead to the Gibbs phenomenon, which you usually try to avoid. And so what we're doing here is a multidimensional optimal order detection. And that just means we do, well, this stuff above here for polynomial orders from 0 to 4. Then we check, starting at the highest order, is there anything that is obviously physically wrong? Say, for example, a negative energy density or something like that. You kick that one out, and from the rest that you then have, you define yet another error measure, and you pick the one with the lowest error. So this is the thing that works actually very nicely, but it's a bit cumbersome to calculate. Now you may wonder, well, does it actually work? Now we have done lots of tests for this, for example, shock tube tests and so on and so forth. We have done neutron stars in Cowling approximation in full GR, and I don't want to go through all of those things in detail. Maybe just one example that is actually in this New Frontiers of GRMHD book. There we thought, let's use our latest version of the code and take one of the standard examples that you find whenever people develop a numerical relativity code. This is a neutron star with a gamma of 2. And you look at the frequencies. And so here we have the densities for a couple of different resolutions. So these are the number of particles that we have here. And then we found these type of frequencies. And we've had one here where we thought, oh, that could actually be yet another frequency. And we then tried to find this in the literature, but we didn't. And then we asked Kostas Kokotas and Nick Sturgiulas, and they didn't know about it either. So they recalculated it and say all of those frequencies here, they agree to substantially better than 1% with what we had found here with our 3D code. And there was zero fine tuning involved. So we just did this before actually we got the numbers from them. Then there is another pretty challenging test, is where you prepare a neutron star that is unstable. And if you just evolve it, it will undergo wild oscillations. If you just do a tiny little bit, you give it a very small invert radial perturbation, then it starts to form a black hole. We could also nicely reproduce that. And then just coming to some recent astrophysics applications. So this is just one example where we looked into mergers of two neutron stars and with only one spinning star. And this is actually pretty well motivated, because if you look at globular clusters, I think the number is something like 70% of the neutron stars in globular clusters have actually a spin of a few milliseconds. And
five minutes left.
Yeah, I'm very close. So and so this is very well motivated, and you have lots of close flybys where you exchange different stars, and you have a pretty good chance that, according to our estimates, that if you have a merging binary system in a about something like 5% of the cases, one of the neutron stars should be very rapidly spinning while the other one is not. And this is now just how the movie looks. Obviously, they have the same mass. So this one, the flattened one, is of course the highly spinning one. And then you just see how that guy is disrupted. And you see it looks a little bit like a merger of two neutron stars that have very different masses, but it's actually both have the same mass here. The only difference is the spin. And there we looked at various multi-messenger signatures of that system. If you're interested in the details, have a look in our paper from last year. Then there's another one from this year, and this is about fast ejector. And if I'm saying fast ejector, these are ejector that have larger velocities than, say, something like 50% of the speed of light. And although this is not much, this may be pretty interesting for the electromagnetic signal because there are a couple of signals related to these fast ejector. And many other groups had seen this as well, but it was actually not so clear where this fast ejector comes from. And since our code is Lagrangian, you can think of this as having a couple of millions of tracer particles. So if you know at the end of your simulation your fast ejector, you can trace back their history and see where they come from. And there we have identified the mechanism, or actually two mechanisms behind getting these fast ejector. And with that, I'm already at the summary. So punchlines here, as I had said, horses for courses. There are things where the best choice is probably really a Eulerian scheme, but for some other questions, there are nice advantages from a method like SPH. One is geometric flexibility, so the particles just go where the matter wants to go. You have exact advection. You don't have a computational volume, so the particles can just go where the particles want to go, and you don't have to bother about vacuum. There's just nothing that you have to do about it. And then I tried to give the basic ideas of our code Sphinx PSSN. And this is a very modern SPH version for the matter. Space-time evolution is a standard PSSN formulation on an adaptive mesh. And well, there are lots of things that are currently going on. And with that, I'm done. Open for questions. And maybe before you ask questions, I do some shameless advertisements about two positions that are open. And as I said, there will be soon an article on the archive. Okay, with that, I'm done. Thank you.
Thank you very much. And thank you very much for the very nice talk. So if anybody has a question, they can raise their hand.